Hello there, and welcome to Sleepy Science Vault. There is a temperature at which the universe simply stops. Not slows down. Not grows quiet. Stops. A point so cold that matter itself would cease to vibrate, where the last trembling motion of the last atom falls completely still. Scientists call it absolute zero, and it sits at minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit. On the Kelvin scale, it is simply zero. Nothing. The bottom of the thermometer. The end of the line. We have never actually reached it. Not in a laboratory, not in nature, not anywhere in the known universe. But we have gotten extraordinarily close, and in doing so, we have glimpsed something strange and almost philosophical, the idea that cold is not just an absence of warmth, but a boundary. A limit written into the laws of physics themselves. At absolute zero, atoms would stop moving entirely. In our everyday world, heat is motion. Every warm cup of tea, every sunlit afternoon, every breath you take, all of it is just atoms and molecules vibrating, bouncing, spinning. The warmer something is, the faster they move. And cold, in the truest sense, is simply the slowing of that motion. Cool a gas and its particles slow down. Cool it further and they slow further still. Approach absolute zero, and they settle into the lowest energy state they are physically permitted to occupy. Not frozen in the way ice is frozen, deeper than that. Quieter than that. The coldest natural temperature ever recorded on Earth was measured in Antarctica, in the East Antarctic Plateau. Satellites detected surface temperatures dropping to around minus 98 degrees Celsius on clear winter nights. That is cold enough to kill in seconds. Cold enough to freeze the moisture in your lungs before you could exhale. And yet, in the grand scale of the universe, it barely registers. There is a cloud of gas drifting through space about 5,000 light-years from Earth, called the Boomerang Nebula. And the Boomerang Nebula makes Antarctica look like a summer afternoon. This dying star, exhaling its outer layers into space at tremendous speed, has cooled itself down to just 1 degree above absolute zero, minus 272 degrees Celsius. It is, as far as we know, the coldest naturally occurring place in the entire observable universe. Colder than the background radiation that fills all of space. Colder than anything our planet has ever come close to producing. A place so still, so empty of thermal energy, that it exists in a category almost entirely its own. That background radiation, the cosmic microwave background, fills every corner of intergalactic space. It is the faint afterglow of the Big Bang, stretched and cooled over 13.8 billion years into a whisper of warmth sitting at just 2.7 Kelvin. Nearly 3 degrees above absolute zero. The vast, dark emptiness between galaxies is not a vacuum of pure nothingness, it is threaded with this ancient, gentle radiation, a reminder that even the coldest reaches of the cosmos carry the memory of an unimaginable heat. And yet, the Boomerang Nebula is colder even than that. Colder than the space between galaxies. Colder than the background hum of the universe itself. It sits at 1 Kelvin, almost perfectly still, almost perfectly silent in a thermal sense, tucked inside a universe that is already almost incomprehensibly cold. Before we travel further into the cosmos, it is worth pausing for a moment closer to home. Within our own solar system, cold takes on forms that feel more tangible, more real, even if no less extreme. Pluto, that small and distant world at the frozen edge of our neighborhood, averages around -225 degrees Celsius. Sunlight reaches it so weakened by distance that it barely warms the surface at all. From Pluto, our sun would look like little more than a very bright star, brilliant, but distant. A source of light more than heat. And yet even Pluto is not the coldest place in the solar system. Deep inside permanently shadowed craters near the moon's poles, craters where sunlight has not touched the ground in billions of years, temperatures have been measured at around -248 degrees Celsius. Colder than Pluto. Colder than almost anywhere in our solar neighborhood. These dark, still pockets on a world we can see with the naked eye hold temperatures that rival the deep outer solar system, simply because no light has reached them since before the dinosaurs existed. Since before complex life existed. Since nearly the beginning of Earth itself. Cold, it turns out, is not just found in distant places. Sometimes it hides in the shadows of familiar ones. And as we move outward from here, past the planets, past the comets, past the slow-drifting debris at the edge of the sun's influence, the universe grows quieter, and colder, and stranger still. Space is not empty. We tend to imagine it that way, a pure, featureless void stretching endlessly between the stars, between galaxies, between everything. But the reality is more textured than that, more layered, filled with thin veils of gas and dust and ancient light. And much of it is extraordinarily, profoundly cold. The darkness between galaxies, that vast intergalactic space where no stars shine nearby and no planet orbits anything, sits at around 2.7 Kelvin. Just a few degrees above absolute zero. It is threaded, as we touched on before, with the cosmic microwave background, that ancient warmth left over from the Big Bang. But beyond that faint radiation, there is very little. Just cold. Just distance. Just the slow, patient expansion of the universe carrying everything further from everything else. Interstellar space, the space between stars within a galaxy like our own Milky Way, is somewhat warmer, depending on where you are. Regions close to active stars can be heated to thousands of degrees by radiation and stellar winds. But in the quieter regions, far from any star's influence, interstellar space settles into temperatures between roughly 10 and 30 Kelvin. Still breathtakingly cold by any human standard, but measurably warmer than the intergalactic emptiness beyond the galaxy's edge. Scattered throughout the Milky Way, however, are regions that fall far below even that. Dark molecular clouds are among the coldest environments our galaxy produces naturally. These are dense concentrations of gas and dust, mostly hydrogen, so thick that starlight cannot penetrate them. From the outside they appear as dark patches against the glow of the galaxy, places where no light escapes and very little enters. Inside, temperatures can drop to as low as 10 Kelvin. The darkness is not just visual. It is thermal. These clouds are cold in a way that is almost total, shielded from the warmth of the stars by their own density, existing in a kind of deep cosmic isolation. And remarkably, some of that coldness drifts closer to home than most people realize. Our solar system is not floating through empty, neutral space. It is moving, as it always has been, through a region of the galaxy that contains thin streams and ribbons of cold interstellar material. One of these is known as the local ribbon of cold clouds, a structure of relatively cool, dense gas that winds through our galactic neighborhood. These clouds are not dangerously close, and they pose no threat to Earth. But they are a reminder that the boundary between our solar system and the wider galaxy is not a sharp line. The cold of interstellar space is not something that stays neatly outside. It drifts and flows, and occasionally brushes up against the edges of our corner of the cosmos. In fact, there is evidence that Earth itself may be passing through one of these cold interstellar clouds right now, or at least very recently has been, in astronomical terms. The Sun's heliosphere, the bubble of solar wind and magnetic field that surrounds our solar system, may be interacting with this cool interstellar material as we move through the galaxy. The effects on Earth's surface are negligible. But the idea itself is quietly remarkable, that our planet, at this very moment, may be threading its way through a ribbon of cold ancient gas that formed long before our solar system existed. The universe, it seems, does not keep its cold at a respectful distance. But of all the cold places scattered across the Milky Way, the shadowed craters, the molecular clouds, the dim interstellar ribbons, one stands out. One has earned a distinction that, as far as current science can determine, belongs to it alone. The coldest known natural place in the entire observable universe is not in some remote galaxy billions of light years away. It is right here, in our own Milky Way, roughly 5,000 light years from Earth. Close, in cosmic terms. Almost neighborly. And it is a place called the Boomerang Nebula. The Boomerang Nebula is a dying star in the process of shedding its outer layers. As stars like our Sun age, they eventually begin to lose their outer envelopes of gas, exhaling them into space in what astronomers call a protoplanetary nebula. The Boomerang is one of these, a star in its final long exhale, releasing gas into the surrounding space at extraordinary speed. And it is that speed that makes it so uniquely, remarkably cold. As the gas expands outward at around 164 kilometers per second, it cools rapidly, the same physical principle that makes aerosol cans feel cold when you spray them. The faster the gas expands, the more dramatically the temperature drops. And in the Boomerang Nebula, the expansion has been so sustained and so rapid that the temperature of the outflowing gas has dropped to approximately 1 Kelvin. 1 degree above absolute zero. That number is worth sitting with for a moment. The cosmic microwave background, the faint warmth that permeates all of intergalactic space, sits at 2.7 Kelvin. The Boomerang Nebula, at 1 Kelvin, is colder than that background radiation. It is colder than the space between galaxies. It is, in effect, colder than the universe's baseline temperature, because the rapid expansion of its gas has stripped away even that residual warmth. In its deep interior, closer to the central star, conditions become even more extreme. the innermost regions of the nebula are thought to reach temperatures approaching the absolute minimum that physics permits. Not absolute zero, nature, as far as we know, never quite reaches that theoretical limit. But close enough that the difference is almost philosophical. Close enough that the atoms there are moving as slowly as atoms in a natural environment are ever observed to move. The Boomerang Nebula is, in a sense, the universe's own experiment in cold. A natural process, a dying star, an expanding cloud of gas, that has accidentally produced conditions more extreme than almost anything we can create in a laboratory. And it sits there, quiet and pale and extraordinarily still, 5,000 light-years away, the coldest thing we have ever found. There may be colder places. The universe is vast, and our observations of it are still incomplete. But for now, the Boomerang Nebula holds the record. A soft, slow-dying star, exhaling its last into the dark, and in doing so, creating something colder than the space between galaxies. Cold, it turns out, can be born from motion. And silence can be the product of a very long, very gradual, very beautiful ending. There is a boundary in the universe that almost nothing crosses. The cosmic microwave background is not just a scientific curiosity. It is, in a very real sense, the thermal floor of the observable universe, the baseline temperature below which the natural cosmos does not go. It fills every cubic centimeter of space, this ancient, faint radiation, left behind by the Big Bang and cooled over nearly 14 billion years to just 2.7 Kelvin. Everywhere you look, in every direction, across every distance we can measure, space is bathed in this whisper of warmth. It is one of the most uniform things in existence. And the Boomerang Nebula sits below it. That single fact is, scientifically speaking, extraordinary. To be colder than the cosmic microwave background means to be colder than the ambient temperature of the universe itself. It means that if you could somehow place this nebula in open intergalactic space, away from any star, in the most remote emptiness imaginable, the background radiation would actually warm it. The universe, at its baseline, is too warm for the Boomerang Nebula. It is the only known natural object with this distinction. Not a laboratory apparatus. Not a carefully engineered quantum cooling experiment. A natural object, formed by ordinary stellar physics, that has managed to undercut the temperature of the universe itself. Every other cold place we know of, dark molecular clouds, shadowed lunar craters, the frozen surface of Pluto, all of them sit above the CMB temperature. All of them are, in the cosmic sense, warmer than the background. The Boomerang Nebula alone drops below that line. More precisely, it is the only known region in the natural universe confirmed to exist below CMB temperature. Not just a point, not just a theoretical calculation, but a measurable volume of space, a cloud of outflowing gas spanning a considerable distance, where temperatures have been observed and confirmed at 1 Kelvin. The measurements have been made, checked, and verified. The Boomerang Nebula is genuinely, observationally, colder than the rest of the universe around it. It is also, as far as current astronomical knowledge confirms, the only preplanetary nebula, that specific class of dying star in the process of shedding its outer layers, ever found to fall below the CMB temperature. Other nebulae of this type exist. Other dying stars exhale their gas into space in similar ways. But none of the others have produced this effect. The combination of outflow speed, duration, and mass loss that created the boomerang's extreme cold appears to be, at minimum, extraordinarily rare. Possibly unique. And so the question naturally arises, where is this thing, and what does it actually look like? The Boomerang Nebula lies in the direction of the constellation Centaurus, one of the large and ancient constellations of the southern sky. Centaurus is most famous for containing Alpha Centauri, the nearest star system to our own Sunday. The Boomerang is much further away than that, far deeper into the galaxy, but it shares the same broad region of sky as seen from Earth. For observers in the southern hemisphere, Centaurus rides high and bright on clear nights, and somewhere within that constellation's boundaries, 5,000 light-years distant, the Boomerang drifts cold and slow in the dark. At 5,000 light-years away, it is not visible to the naked eye. Even a modest backyard telescope will not reveal it. Observing the Boomerang requires serious equipment. It was studied in detail using the Hubble Space Telescope, which captured images of it with a clarity that ground-based instruments simply cannot match. Those Hubble images revealed something unexpectedly beautiful, a pale, hourglass-shaped cloud of gas glowing softly against the darkness, symmetrical and ghostly, lit not by its own emission but by the light of the star at its center. It is what astronomers call a reflection nebula. The gas itself does not glow, it reflects. Like fog illuminated by a distant streetlight. The nebula spans approximately 1 light-year in diameter. That sounds large, and in human terms it is almost incomprehensibly so. A light-year is roughly 9.5 trillion kilometers. But in the context of interstellar space, 1 light-year is a relatively compact structure. The Boomerang is not a sprawling, diffuse cloud spread across dozens of light-years like some nebulae. It is contained, relatively dense, and coherent in its structure, a distinct and recognizable shape floating in the dark. At its heart sits a dying star. The central star of the Boomerang Nebula is what astronomers classify as a red giant, or more accurately, a star in the late stages of its red giant phase, in the process of expelling its outer layers into space. This is not a dramatic explosion. It is a long, slow release, the star gradually losing its outer atmosphere over thousands of years, the gas streaming outward in a continuous flow. The star is no longer fusing hydrogen in any stable way. It is running down, its energy output becoming erratic, its layers loosening their gravitational grip and drifting away. What makes this quietly moving is the star's past. The central star of the Boomerang Nebula was once, in all likelihood, a great deal like our own Sunday. Not identical, perhaps slightly more massive, but similar in the ways that matter, a main sequence star, burning steadily, radiating warmth into the space around it. For billions of years it lived that ordinary stellar life. And now it is ending, shedding itself into the dark, and in doing so, creating the coldest known place in the observable universe. Our own sun will do something similar, in about 5 billion years. It will swell into a red giant, engulf the inner planets, and eventually shed its outer layers as a planetary nebula. The details will differ, whether it will cool as dramatically as the Boomerang remains unknown. But the broad story is the same. What we are looking at, in the Boomerang Nebula, is a possible distant mirror of our own sun's future. A star that once shone the way ours does now. A star that warmed whatever surrounded it for billions of years. And now, in its ending, that same star has become the coldest thing in the universe we know of. There is something almost meditative in that reversal, that the conclusion of a stellar life, the final long exhale of a sun-like star, could produce not warmth, but the most profound cold we have ever measured. The universe contains multitudes. And sometimes the most remarkable things it produces are not the result of violence or explosion, but of something much quieter. A slow release. A gradual cooling. A star letting go. When a star like our sun reaches the end of its long life, it does not go quietly in the way we might imagine. There is no sudden collapse, no violent implosion, no dramatic farewell. Instead, it swells. Over millions of years, the outer layers of the star expand outward into space, growing cooler and dimmer as they go, until the star has transformed into something vast and diffuse, a red giant many times its original size, its outer atmosphere barely held together by gravity. Eventually, those outer layers are released entirely. The star exhales its remaining envelope into the surrounding space, and what is left behind is a slowly expanding shell of gas surrounding a small, hot, exposed stellar core. When that shell of gas catches the ultraviolet light from the hot core and begins to glow, we call it a planetary nebula. The name is historical and slightly misleading. Planetary nebulae have nothing to do with planets. Early astronomers, observing them through small telescopes, thought their round, glowing shapes resembled the disk of a planet. The name stuck. But what they actually are is something far more significant, the beautiful, glowing remnant of a star's final act. The Boomerang Nebula has not quite reached that stage. It is classified as a preplanetary nebula, sometimes called a protoplanetary nebula, a star caught in the transition between red giant and full planetary nebula. The central star has begun shedding its outer layers, and the gas is streaming outward, but the exposed core has not yet become hot enough to ionize the surrounding gas and make it glow on its own. The shell is there. The outflow is there. But the light show has not yet fully begun. The boomerang exists in an in-between state, a chrysalis stage in the life of a dying star, neither fully what it was nor yet fully what it will become. This makes it relatively young, in the context of stellar evolution. Preplanetary nebulae are short-lived phenomena on astronomical timescales. The transition from red giant to glowing planetary nebula can happen over a few thousand to tens of thousands of years, an eye blink compared to the billions of years a star spends in its main sequence life. The boomerang is estimated to be quite young even within that narrow window. Astronomers believe the dramatic outflow that created its extreme cold has been occurring for only a few thousand years. In human terms, that sounds like a long time. But consider that human civilization has existed for roughly the same duration, and that our sun has been burning for nearly 5 billion years. The boomerang's current phase is extraordinarily brief. We are catching it, in a sense, at a very particular and fleeting moment in its long stellar story. The cooling that produced its record-breaking temperature happened within this same short window. The rapid outflow of gas, expanding at around 164 kilometers per second, has been underway for perhaps a few thousand years, and it is that sustained, rapid expansion that has driven the temperature down to 1 Kelvin. In cosmic terms, this process happened almost recently. The cold that makes the boomerang unique is not ancient. It is, relatively speaking, new. A few thousand years ago, this region of space was warmer. The outflow began, the gas expanded, and the temperature plummeted. What we observe now is the result of that ongoing process, still active, still cooling, still extraordinary. There is something quietly striking about that timeline. While human beings were building early cities, developing writing, raising the first monuments of organized civilization, somewhere in the constellation Centaurus, a dying star was beginning to exhale its outer layers into space, and the coldest known place in the universe was, slowly and silently, coming into being. The universe has its own calendar, and it runs on scales that dwarf our own. But occasionally, the two timelines overlap in ways that are worth noticing. Now, beyond its temperature, the Boomerang Nebula has another quality that draws attention: its appearance. Because the way it looks is, by astronomical standards, genuinely unusual. The nebula was first observed in 1980 by astronomers Keith Taylor and Mike Scarrett, using a telescope in Chile. When they examined their data, they noted that the faint cloud of gas surrounding the central star appeared to have an asymmetric, curved shape, something that loosely resembled a boomerang. The name was given informally at first, as these things often are in astronomy, but it persisted. The Boomerang Nebula had its identity. Later observations, particularly those made with the Hubble Space Telescope, revealed that the earlier description had been somewhat incomplete. The full structure of the nebula, seen with Hubble's resolution, does not look like a simple curved arc. It looks like an hourglass. Two broad lobes of gas extend outward from the central star in opposite directions, connected at the middle by a narrower waist. The overall form is symmetrical in a way that feels almost deliberate: two roughly equal expansions, pushing outward in opposite directions, creating that characteristic pinched middle shape. This kind of bipolar structure is actually not uncommon in planetary and preplanetary nebulae, though the Boomerang's version is particularly well defined. The shaping of these lobes is thought to be driven by stellar winds, streams of particles and energy flowing outward from the central star. In many cases, the star at the center of a dying nebula is not alone. A companion star, or even a disk of orbiting material, can redirect the outflowing gas, channeling it preferentially along certain axes and creating the lobed, hourglass shapes we observe. The gas does not simply expand in a perfect sphere, because the forces acting on it are not uniform. They push and pull and redirect, sculpting the cloud into something that, seen from the right angle, looks almost structured, almost intentional. The boomerang's hourglass is thought to have been shaped by exactly these kinds of mechanisms: stellar winds interacting with the surrounding environment, possibly influenced by a companion object or a disk of material close to the central star. The result is the pale, symmetrical structure that Hubble captured so clearly. But there is something unusual about the way the boomerang appears in different kinds of light. Invisible light, the light our eyes can see, the light that most telescopes traditionally collected, the boomerang is nearly invisible. It is extraordinarily faint, a ghostly smudge if it can be detected at all. This is partly because it is a reflection nebula at this stage, not an emission nebula. It does not glow with its own light. It reflects the light of its central star, and the central star, while still present, does not yet produce the intense ultraviolet radiation that would make the surrounding gas shine brightly. The result is a cloud that is invisible wavelengths, almost transparent. Easy to overlook. Easy to miss. This is part of why early observations gave an incomplete picture of the nebula's true shape. Working in visible light, with the technology available in 1980, astronomers were seeing only a hint of the structure. The full form was hidden, washed out, barely there. It is in other wavelengths, particularly radio waves and millimeter wavelengths, that the boomerang reveals itself more fully. Radio astronomy, which detects the long wavelength emissions of cold gas rather than visible light, can see into structures that are optically dark. And it is through radio observations that much of what we know about the boomerang's temperature, composition, and outflow speed has been measured. The nebula that is nearly invisible to the human eye, in the spectrum our eyes evolved to see, turns out to be rich in detail and structure when observed in the right way. This is a recurring theme in modern astronomy. The universe looks very different depending on how you look at it. The sky we see on a clear night is only one layer of reality. Beneath it, in wavelengths from radio to X-ray, the same sky contains storms and whispers and structures entirely invisible to unaided human perception. The Boomerang Nebula is a particularly vivid example of that truth. Optically faint, almost hidden, but unmistakably present when the right instruments are turned its way. There is a kind of lesson in that, if you are inclined to find one. The coldest, most remarkable things are not always the most obvious. Sometimes the most extraordinary places in the universe are the ones that barely show up in ordinary light. And what the boomerang offers, once you look at it in the right way, is a portrait of transformation, a star caught between what it was and what it is becoming, wrapped in a pale hourglass of its own exhaled atmosphere, cooling steadily toward the closest thing nature produces to absolute silence. It drifts there now, 5,000 light-years away, neither fully visible nor fully invisible. A dying star in a cold cloud, shaping itself slowly into something new. Not gone. Not yet arrived. Somewhere beautifully in between. The universe is full of transitions like this. Full of things that are ending and beginning simultaneously, full of structures caught in the middle of becoming something else. We tend to think of space as static, a fixed backdrop of stars and darkness. But it is not static at all. It is changing, always, at every scale, from the grand sweep of galactic evolution down to the quiet, gradual exhale of a single aging star. The boomerang reminds us of that. And in doing so, it earns its place not just as a scientific curiosity, but as one of the more quietly remarkable objects in the known universe. Seeing the Boomerang Nebula is not a straightforward task. Even with a capable telescope, pointing toward the right patch of sky in Centaurus and expecting a clear, vivid view is likely to leave you disappointed. In optical light, the visible spectrum, the wavelengths our eyes evolved to detect, the boomerang is elusive. It is faint in a way that goes beyond simple distance. The cloud of outflowing gas that makes up the nebula does not emit its own light in any meaningful way at this stage of its evolution. It reflects, dimly, the light of the star at its center. And that star, while still present and still radiating, has not yet reached the temperature needed to flood its surroundings with the kind of energetic ultraviolet light that would make the gas glow brightly and independently. The result is a nebula that, in ordinary visible light, is barely there. Hubble could capture it with long exposures and exceptional sensitivity, and those images are genuinely beautiful. But the boomerang does not announce itself. It does not blaze. It sits in the sky like a whispered sentence, present and meaningful, but requiring patience and the right kind of attention to hear properly. That right kind of attention, for the boomerang, means radio wavelengths. Radio astronomy sees the universe in an entirely different register. Where optical telescopes detect the photons our eyes can process, radio telescopes listen for the long, slow oscillations of electromagnetic radiation emitted by cold gas, molecules drifting in space, and the subtle signatures of physical processes that produce no visible light at all. Cold hydrogen, carbon monoxide, and other molecular species that pervade interstellar clouds all emit characteristic radio signatures, and these are exactly the kinds of materials that fill the outflowing envelope of the Boomerang Nebula. It was through radio and millimeter wave observations that astronomers were able to measure the boomerang's temperature with confidence. The spectral lines of carbon monoxide molecules, detected at millimeter wavelengths, revealed the extraordinary coldness of the gas. Radio observations also helped establish the outflow velocity, the mass loss rate, and the overall structure of the nebula in ways that visible light simply could not. In the radio sky, the boomerang is a far more legible object, its properties readable, its extremity measurable, its record-breaking cold unmistakable. This is worth dwelling on for a moment, because it illustrates something important about how science is actually done. The most significant discovery about the Boomerang Nebula, the fact that it is the coldest known natural place in the universe, was not made by looking at it. It was made by listening to it, in a sense. By detecting the faint molecular signals it emits in a part of the electromagnetic spectrum completely invisible to human eyes. The universe does not reveal its most extreme secrets through ordinary observation. It reveals them to instruments designed to detect what our senses cannot reach. The boomerang was hiding in plain sight, in a part of the sky that had been observed for decades, its most remarkable property undetectable until the right instruments were pointed its way. That is a recurring pattern in the history of astronomy, and it suggests, quietly but persistently, that the universe still contains surprises we cannot yet detect, waiting for instruments that do not yet exist. But once those measurements were made, the question became unavoidable: why? Why is the Boomerang Nebula so cold? What process, operating within the ordinary physics of a dying star, could produce temperatures lower than the background temperature of the universe itself? The answer lies in a phenomenon called adiabatic cooling. It is the same basic principle that makes a pressurized aerosol can feel cold when you spray it, or that makes the air rushing out of a bicycle tire feel cool against your hand. When a gas expands rapidly without exchanging heat with its surroundings, it cools. The molecules spread out, their collisions become less frequent, their average kinetic energy drops. The temperature falls. This is not a mysterious or exotic process, it is a straightforward consequence of thermodynamics, observable in everyday life. In the Boomerang Nebula, this same process operates at a scale and intensity that is almost impossible to fully comprehend. The dying star at the center is not simply releasing gas slowly and gently. It is ejecting its outer layers at extraordinary speed, around 164 kilometers per second. To put that in perspective, 164 kilometers per second is roughly 590,000 kilometers per hour. A jet airliner travels at about 900 kilometers per hour. The gas streaming outward from the Boomerang's central star is moving at more than 650 times that speed. At this velocity, the expansion of the gas is so rapid, and the consequent cooling so dramatic, that the temperature of the outflowing material drops far below anything the surrounding space can replenish. In an ordinary nebula, the expanding gas would cool somewhat, but the surrounding radiation, including the cosmic microwave background, would gradually warm it back toward equilibrium. In the Boomerang, the expansion is fast enough, and the outflow dense enough, that the gas cools faster than the universe can warm it. It falls below the CMB temperature and keeps going. This is why astronomers sometimes describe the Boomerang Nebula as a kind of cosmic refrigerator. Not because something is deliberately cooling it from outside, but because the rapid expansion of its own gas is driving its temperature down through a natural thermodynamic process. The refrigerator analogy is imperfect, as all analogies are, but the underlying principle is genuine. In a refrigerator, a gas is compressed and then allowed to expand, and the expansion removes heat from the surrounding space. In the Boomerang, the gas expelled from the star expands into the surrounding void, and in doing so, removes thermal energy from itself at a rate that the universe cannot compensate for. The cold wind streaming outward from the Boomerang's central star is not a metaphor. It is a measurable physical reality, a sustained, high-speed outflow of gas that has been dramatically lowering the temperature of the surrounding nebula for thousands of years. And it continues now, at this moment. The star is still losing mass. The gas is still expanding. The cooling is still ongoing. What makes the Boomerang particularly extreme, even among dying stars, is not just the speed of its outflow but the rate at which it is losing mass. Dying stars routinely shed material as they evolve, that is, in one sense, what makes them dying stars. But the Boomerang's central star is losing mass at a rate approximately 100 times faster than other stars in a similar evolutionary stage. Most protoplanetary nebulae involve mass loss rates of a certain range. The Boomerang sits far outside that range, shedding material at a pace that is, among known objects of its type, exceptional. Over the course of its outflow, the Boomerang's central star is estimated to have already lost approximately 1.5 solar masses of material. One solar mass is the mass of our entire sun, all of it, Every atom of hydrogen and helium and trace elements, the entire vast ball of stellar material that has been fusing for nearly 5 billion years. The boomerang has expelled the equivalent of 1.5 of those into space at 164 kilometers per second. Over a few thousand years. That is an almost staggering quantity of material, released at an almost staggering rate. And it is the combination of these factors, the speed, the sustained rate, the sheer volume of gas, that produces the record-breaking cold. Any one of these elements alone would create a cold nebula. Together, they create something colder than the universe around it. It is worth stepping back for a moment to appreciate what this means in physical terms. The Boomerang Nebula is not cold because it is in a special location, far from any source of energy. It is cold despite being in a galaxy full of stars, relatively close to the galactic plane, in a region that is by no means exceptionally remote or shielded. The background radiation that permeates all of space reaches the boomerang just as it reaches everywhere else. The light of distant stars, the cosmic radiation from countless sources, none of it is blocked from this region. And yet the gas is 1 Kelvin. Because the expansion is simply too fast, too sustained, and too voluminous for any of that ambient energy to compensate. The thermodynamics of rapid adiabatic expansion overwhelm everything else. The universe tries, in its quiet way, to warm the boomerang back toward equilibrium, and the boomerang's own physics push back harder. There is something almost poetic about that dynamic, a dying star, in its final long exhale, generating a cold so intense that the universe itself cannot counteract it. Not through any special property of the star. Not through any unusual location or shielding. Simply through the act of letting go, quickly and abundantly and with extraordinary force. The cold of the boomerang is not a feature of emptiness. It is a feature of motion. Of gas moving outward faster than heat can follow. Of expansion outpacing equilibrium. Of a natural process, operating within completely ordinary physics, producing an outcome that is anything but ordinary. In laboratories on Earth, physicists work enormously hard to achieve temperatures near absolute zero. They use lasers to slow individual atoms. They use magnetic fields to trap ultracold gases. They use dilution refrigerators, carefully engineered and meticulously maintained, to push temperatures into the millikelvin range. These are extraordinary achievements of human ingenuity, and they have produced remarkable science. And yet, 5,000 light-years away, a star that never knew we existed has done something comparable through nothing more than the physics of its own dissolution. Colder than our best laboratory temperatures? Not quite. Human technology has achieved temperatures even lower than 1 Kelvin under controlled conditions. But colder than anything nature has produced that we have ever found? Yes. Without question. The Boomerang Nebula is what happens when a very ordinary physical process, a gas expanding into space, is pushed to an extraordinary degree. It is a reminder that the universe does not need exotic mechanisms or unusual conditions to produce extreme results. Sometimes it just needs enough of something very simple. In this case, speed, and time, and a star willing to give almost everything it has left. The cold inside the Boomerang Nebula is not uniformly distributed. As the gas streams outward from the central star, it does not escape in a perfectly smooth, even flow in every direction. The structure of the nebula, that hourglass shape, those two broad lobes connected at a narrower middle, tells us that the outflow is channeled. The gas moves preferentially through certain paths, and in particular, it accelerates through the narrower regions of the nebula's structure, the pinched points where the geometry of the outflow concentrates the expanding material. Through these constrictions, the gas moves even faster than the average outflow speed, and faster expansion means even more dramatic cooling. These narrow exit points act almost like nozzles, in a physical sense. The same principle appears in many contexts. Gas forced through a restriction accelerates, and accelerating gas cools. In the Boomerang, this effect compounds the already extreme adiabatic cooling of the broader outflow, creating pockets and channels within the nebula where temperatures may be even lower than the measured average. The cold is not a single uniform state throughout the cloud. It is a landscape, with gradients and channels, shaped by the geometry of the dying star's exhalation. And within that landscape, something remarkable is happening at a molecular level. The Boomerang Nebula, despite being the coldest known natural place in the universe, is not simply losing heat into the void around it. It is also, in a sense, actively absorbing warmth from its surroundings, and that warmth is not enough to make a meaningful difference. The cosmic microwave background radiation, that faint 2.7 Kelvin glow that permeates all of space, does reach the Boomerang. Its photons travel through the outflowing gas just as they travel through everything else. And at 1 Kelvin, the gas in the nebula is colder than this radiation, which means that thermodynamically, the CMB is actually transferring energy into the nebula rather than being cooled by it. The universe is, technically, warming the Boomerang, just not fast enough to matter. The rate of energy transfer from the CMB into the nebula's gas is simply overwhelmed by the ongoing cooling from rapid expansion. The star continues to shed material. The gas continues to expand. The adiabatic cooling continues to drive temperatures down. The universe nudges the Boomerang gently back toward equilibrium, and the Boomerang's own physics refuse. For now, at least, the expansion wins. But what happens to the molecules within this extraordinary cold? At 1 Kelvin, the behavior of matter changes in ways that go beyond simply being very cold. Gases that we think of as essentially permanent, substances that remain gaseous across a wide range of temperatures, begin to do something unexpected. They freeze. Oxygen, under normal circumstances, becomes liquid at around 90 Kelvin and solid at around 54 Kelvin. These are cold temperatures by human standards, but they are far above 1 Kelvin. In the coldest regions of the Boomerang Nebula, oxygen does not remain as a gas. It freezes. The oxygen atoms and molecules within the outflowing gas are cold enough to condense onto dust grains, forming a thin coating of solid oxygen ice on the tiny particles that drift through the cloud. This is not the familiar water ice of comets or polar regions. This is elemental oxygen, solidified by cold that barely exists elsewhere in nature. Carbon monoxide behaves similarly. This molecule, which is one of the primary tracers that radio astronomers use to study cold interstellar gas, freezes at around 68 Kelvin under low-pressure conditions. In the Boomerang, well below that threshold, carbon monoxide can condense onto dust grain surfaces, becoming part of the icy mantles that coat the solid particles suspended in the outflow. Nitrogen, another normally gaseous element, freezes at around 63 Kelvin, also far above the Boomerang's temperature, and also capable of freezing onto grain surfaces in these conditions. The Boomerang Nebula, in its coldest regions, is a place where gases that exist nowhere else in solid form are quietly crystallizing onto dust. A slow, silent precipitation of frozen molecules in the dark. The cloud is not just cold in the abstract, thermometric sense. It is cold in a way that physically transforms the matter within it, changing the state of substances that remain gaseous almost everywhere else in the observable universe. This molecular behavior is part of what makes the Boomerang scientifically valuable beyond its record-breaking temperature. By studying how molecules behave in environments this cold, astronomers and physicists gain insight into chemistry and physics that cannot be replicated in a laboratory at this scale. The Boomerang is, in a sense, a natural cold laboratory, operating at temperatures and spatial scales no human-built facility could approach. But as remarkable as the Boomerang's current state is, a question has long hovered over it. Why is this particular star behaving so differently from other dying stars? The mass loss rate is far higher than typical. The outflow speed is extreme. The cooling is unprecedented. What is driving this? What makes the Boomerang so exceptional when most stars of similar type do not come close to these conditions? The leading explanation involves not one star, but two. Astronomers have proposed that the extraordinary outflow from the Boomerang's central star may be the result of a binary stellar interaction, a gravitational and physical encounter between the primary star and a companion. In this scenario, the dying red giant at the center of the Boomerang was not always alone. It had a companion star, orbiting nearby, and at some point in the relatively recent astronomical past, within the last few thousand years, that companion star spiraled inward toward the primary. As the companion approached and eventually plunged into the outer envelope of the red giant, the energy of that interaction was transferred to the surrounding gas. The gravitational and kinetic energy of the in-spiraling companion essentially launched the outer layers of the primary star outward at tremendous speed. The companion's plunge acted like a sudden, enormous injection of energy into the star's envelope, driving the mass loss rate to extraordinary levels and accelerating the outflow far beyond what a single dying star would produce on its own. This is not a gentle process. The merger or deep interaction of two stars is among the more dramatic events in stellar astronomy. But it produces exactly the conditions we observe in the Boomerang: a very high outflow velocity, an exceptional mass loss rate, and the bipolar, structured shape of the nebula, which is consistent with the kind of asymmetric ejection that a binary interaction would produce. In 2017, a detailed study using the Atacama Large Millimeter Array, one of the most powerful radio telescope facilities on Earth, located in the high desert of Chile, provided significant support for this picture. The observations revealed a structure within the Boomerang consistent with the aftermath of a binary interaction, including evidence of material distributed in ways that are difficult to explain with a single-star model. The study did not close the question entirely. Stellar evolution is complex, and the details of binary interactions are still an active area of research. But it strengthened the case considerably. The most likely explanation for why the Boomerang is so cold is that it is the product of two stars, not one, a collision or merger that injected enormous energy into the system and paradoxically produced the coldest known place in the universe. There is an irony in that which is hard to overlook. The coldest natural object we have ever discovered was, in all likelihood, born from one of the most energetic types of stellar event. An enormous release of gravitational energy, two stars interacting at close range, translated, through the mechanics of rapid gas expansion, into a cold more extreme than the background temperature of the universe. Energy and cold, cause and effect, separated by the elegant physics of adiabatic expansion. But the Boomerang is not a static object, frozen in its current extreme state forever. It is evolving. The outflow continues, and as it does, the nebula expands outward into the surrounding interstellar medium. As the gas spreads over a larger and larger volume, its density decreases. And as the density decreases, the rate of adiabatic cooling also changes. The conditions that currently produce 1 Kelvin temperatures will not last indefinitely. There is evidence to suggest that the Boomerang may already be warming in its outer regions, even as its inner regions remain extraordinarily cold. As the expanding gas encounters the ambient interstellar medium, and as the central star's radiation slowly increases in intensity as the star evolves toward its next phase, the energy balance within the nebula will shift. The cooling will become less dominant. The CMB and other sources of ambient radiation will begin to gain the upper hand. Over thousands of years, a short time, astronomically speaking, the Boomerang will continue to change. The central star will eventually shed its remaining outer layers entirely, exposing the hot, compact stellar core beneath. That core will radiate intensely in ultraviolet wavelengths, and that radiation will begin to ionize the surrounding gas. The reflection nebula will become an emission nebula. The ghostly, barely visible hourglass will brighten into a glowing planetary nebula, adding its own small contribution to the gallery of stellar endings scattered throughout the Milky Way. And at that point, the record-breaking cold will be gone. The gas will have warmed. The frozen molecules on dust-grained surfaces will have sublimated back into gas. The nebula that is currently colder than the universe around it will have rejoined the ordinary temperature range of interstellar space. The Boomerang will still be beautiful, probably. Planetary nebulae often are. But it will no longer be unique in the way it is unique now. What remains at the very end of this process, after the gas has dispersed and the glow has faded, will be a white dwarf, the exposed, slowly cooling core of what was once a star. Not entirely unlike our Sun, white dwarfs are extraordinary objects in their own right, roughly the mass of our Sun compressed into a volume approximately the size of Earth, supported not by nuclear fusion but by the quantum mechanical pressure of electrons resisting compression. They cool over billions of years, radiating their stored heat into space, growing dimmer and colder across timescales that dwarf the current age of the universe. The white dwarf that the Boomerang's central star will eventually become will carry within it no record of what it once produced. It will not be cold. It will not be remarkable in the way the Boomerang is remarkable now. It will be one of hundreds of billions of white dwarfs that the Milky Way will eventually contain, quiet, small, slowly fading, an ember where a fire once burned. But right now, in this brief window of cosmic time, the star is still in its extraordinary middle phase. Still shedding. Still driving that cold wind outward at 164 kilometers per second. Still producing, in the expanding cloud around it, the coldest temperatures the natural universe has ever shown us. The Boomerang Nebula is not permanent. Nothing in the universe is. But what it is right now, in this fleeting astronomical moment, is something genuinely without equal. And there is something worth appreciating in that, the fact that we exist at the right time, with the right instruments, to have found it at all. The story of how we came to know the Boomerang Nebula for what it truly is did not unfold all at once. It was not a single dramatic moment of discovery, a scientist at a telescope, suddenly realizing they were looking at the coldest place in the universe. It was, like most genuine scientific understanding, a gradual accumulation. A series of observations, separated by years and sometimes decades, each one revealing a little more of the picture, until eventually the full portrait came into focus and the significance of what had been found became undeniable. The beginning was modest. In 1980, astronomers Keith Taylor and Mike Scarrett were conducting observations using a telescope at the Anglo-Australian Observatory in Chile. They detected a faint nebula, a small, dim cloud of gas, in the direction of the constellation Centaurus. The shape of the cloud appeared asymmetric and slightly curved, and so they gave it the informal name that has stayed with it ever since. The Boomerang Nebula entered the astronomical record as an interesting but not yet extraordinary object. A faint nebula among many faint nebulae, noted, catalogued, and set aside for future study. At this stage, there was no way to know what the Boomerang truly was. The instruments of 1980 were not equipped to measure the temperature of a cold molecular cloud at this distance with the precision required to reveal its extraordinary nature. The discovery was real, but it was incomplete in the way that first discoveries almost always are. A door had been opened, but the room beyond was still dark. What eventually illuminated that room was not a new telescope, at first. It was a new way of thinking about what to look for. The cosmic microwave background radiation is not just a passive presence in the universe. Because it permeates all of space, it interacts with matter it passes through. When CMB photons travel through a cloud of cold gas, they can be absorbed by the molecules in that gas, but only if the gas is colder than the radiation itself. If the gas is warmer than 2.7 Kelvin, the CMB passes through more or less freely, or is even slightly scattered or re-emitted. But if the gas is colder than the CMB, the molecules in the gas will absorb those photons, because they represent an energy source above the gas's own temperature. The cold gas effectively drinks in the background radiation. This absorption leaves a detectable signature. When astronomers observe a region of sky containing a very cold molecular cloud, they can, under the right conditions, see the shadow of that absorption against the background, a dimming of the CMB in the direction of the cloud, caused by the cold gas pulling energy out of the passing radiation. This is a subtle effect, difficult to detect and easy to miss. But it is a genuine physical signal, and it carries a direct implication. Any cloud that absorbs the CMB in this way must be colder than the CMB itself. It must be below 2.7 Kelvin. Detecting this kind of CMB absorption in the direction of the Boomerang Nebula was the first real indication that something genuinely unusual was happening there. The signal said, unmistakably, that the gas in this region was not merely cold in the ordinary interstellar sense. It was colder than the background radiation of the universe. The implications of that detection were significant enough to demand follow-up, careful, systematic measurements to confirm and quantify what the absorption signal was suggesting. That follow-up came in the mid-1990s, when astronomers Raghavendra Sahai and Lars-Åke Nyman turned more sensitive radio instruments toward the boomerang and made the measurements that would establish its place in astronomical history. Using the Swedish ESO submillimeter telescope, also located in Chile, they observed the spectral signatures of carbon monoxide molecules within the nebula at millimeter wavelengths. These molecular lines are exquisitely sensitive to temperature. The precise shape and strength of the emission or absorption features in the spectrum encodes information about how cold the gas is. And what Sahai and Nyman found was unambiguous. The gas in the Boomerang Nebula was at approximately 1 Kelvin, 1 degree above absolute zero, below the temperature of the cosmic microwave background, below the temperature of anything else in the known natural universe. Raghavendra Sahai, an astronomer at NASA's Jet Propulsion Laboratory, became one of the central figures in the ongoing study of the boomerang and the broader scientific understanding of what it represents. His work on the nebula spanned years, involving multiple telescopes and multiple wavelengths, each set of observations adding depth and clarity to the picture. Sahai brought not just technical skill to this work but a sustained focus on understanding what made the boomerang unique, what physical processes could account for its temperature, its structure, and its extraordinary mass loss rate. The boomerang is, in no small part, as well understood as it is today because of the persistence and rigor he and his collaborators brought to its study. But measurements from ground-based radio telescopes, however careful and well-conducted, have their limitations. The atmosphere blurs and absorbs certain wavelengths. Angular resolution, the ability to distinguish fine spatial detail, is constrained by the size of the telescope and the wavelength being observed. To see the boomerang's structure clearly, to map its shape and understand the geometry of its outflow, required an instrument above the atmosphere. It required Hubble. The Hubble Space Telescope observed the Boomerang Nebula and produced images that showed its structure with a clarity that ground-based instruments could not match. In visible and near-infrared light, Hubble revealed the pale hourglass form that has since become the boomerang's most recognizable feature: two lobes of reflected starlight, symmetrically arranged, connected at the middle, the whole structure glowing softly against the dark background of space. These images were striking not just for their aesthetic quality but for what they revealed about the nebula's geometry. The bipolar structure, the orientation of the lobes, the overall symmetry of the outflow, all of it became legible in a way it had not been before. Hubble also confirmed that the Boomerang is a reflection nebula at this stage of its evolution. The images showed that the gas cloud does not glow with its own emission but shines by reflecting the light of the central star, like a thin fog illuminated from within. This was consistent with the pre-planetary nebula classification and with the understanding that the central star had not yet developed the intense ultraviolet output needed to ionize the surrounding gas. The Hubble images put a face on the Boomerang, a recognizable, structured, beautiful face, and made it possible to discuss its appearance in geometry in concrete terms. Later, the Spitzer Space Telescope, NASA's infrared observatory, which operated in the thermal infrared rather than visible light, added another layer to the portrait. Infrared observations are sensitive to warm dust and to the thermal emission of structures that are invisible in optical light. Spitzer's observations of the Boomerang helped map the distribution of dust within the nebula, providing information about the solid particles that are mixed in with the cold gas. Dust plays an important role in the Boomerang story. It is on the surfaces of these tiny solid grains that molecules like carbon monoxide and oxygen are freezing out, building up those thin icy mantles we considered earlier. Spitzer could not directly observe the frozen molecules, but its infrared data helped build a more complete three-dimensional picture of the nebula's physical structure. Each of these telescopes contributed something distinct and necessary. Hubble gave shape. Spitzer gave thermal structure. Ground-based radio telescopes gave temperature and molecular composition. But to make the most precise and detailed measurements of the Boomerang's cold gas, to confirm with the highest available precision that the temperature was indeed below the CMB, and to study the fine structure of the outflow in detail, one more instrument was needed. And that instrument would prove to be the most powerful yet. The Atacama Large Millimeter Array, known as ALMA, is not a single telescope but an array of 66 high-precision radio antennas spread across the Atacama Desert in northern Chile, at an altitude of roughly 5,000 meters. At that elevation, above most of the water vapor in the atmosphere, ALMA can observe millimeter and sub-millimeter wavelengths with a sensitivity and resolution that no previous facility could approach. It is, for the study of cold molecular gas in space, essentially the most powerful instrument humanity has ever built. When ALMA was turned toward the Boomerang Nebula, the results were extraordinary in their detail. The array's high angular resolution allowed astronomers to map the distribution of cold gas within the nebula at a level of precision that simply had not been possible before. The molecular line emissions from carbon monoxide and other species were resolved spatially, meaning astronomers could see not just the average temperature of the nebula but how the temperature varied across its structure. They could trace the outflow, map its velocity, identify the regions of most extreme cold, and study the asymmetries that suggested the influence of a binary companion. The ALMA observations also provided the most rigorous confirmation yet of the CMB absorption signature. The cold gas in the Boomerang absorbs background radiation in a way that is clearly and measurably below the CMB temperature, and ALMA's sensitivity allowed this to be confirmed with a precision that left no reasonable doubt. The Boomerang was not approximately colder than the CMB, or borderline colder, or colder within the margin of error. It was definitively, clearly, measurably colder. In 2013, Drawing on the accumulated weight of all these observations, the original radio measurements of Sahay and Nyman, the Hubble imaging, the Spitzer infrared data, and the new ALMA measurements, the Boomerang Nebula was formally confirmed as the coldest known natural object in the observable universe. The confirmation was not a press release or a dramatic announcement in the usual sense. It was a scientific paper, carefully written, presenting carefully gathered data, reviewed by other scientists, and published in a journal. That is how science actually enshrines its discoveries, not with fanfare, but with evidence laid out patiently for scrutiny. But the significance of that confirmation was real. After more than 3 decades of increasingly sophisticated observation, beginning with a vague curved smudge detected by 2 astronomers in Chile in 1980, the Boomerang Nebula had been established as something genuinely without precedent in the natural universe. A dying star, 5,000 light-years away, producing temperatures lower than the background temperature of the cosmos itself. It is worth reflecting, for a moment, on the arc of that discovery. 33 years separated the first detection of the boomerang as a faint optical nebula and the definitive confirmation of its record-breaking temperature. In that time, the telescopes we used to study it improved beyond recognition. The detectors, the analysis techniques, the theoretical understanding of stellar evolution and molecular astrophysics, all of it advanced enormously. And each advance revealed a little more of what the boomerang truly was, until the full picture was finally assembled. This is the normal pace of deep scientific understanding. Not a sudden revelation but a slow convergence, instrument by instrument, observation by observation, toward a truth that was always there, waiting in the cold dark of the constellation Centaurus, patient and indifferent to whether we ever found it at all. The universe does not care if we understand it, but it rewards the effort, slowly and on its own terms, with glimpses of things that are genuinely astonishing. The Boomerang Nebula is one of those things. And the story of its discovery is, in its quiet way, as remarkable as the object itself, a testament to decades of careful work, accumulated knowledge, and the steady, unhurried persistence of scientific curiosity. There is something almost restful in that idea. The answers were always out there. We simply had to build the right instruments, ask the right questions, and wait long enough to hear the reply. The Boomerang Nebula did not become famous overnight. Its recognition as the coldest known natural place in the observable universe was not the kind of discovery that produces immediate headlines and widespread attention. The measurements made by Sahay and Nyman in the mid-1990s established its extraordinary temperature, and subsequent observations refined and confirmed that understanding over the following years. But it took time, the slow accumulation of evidence, the gradual building of scientific consensus, and eventually the definitive ALMA confirmation in 2013, before the boomerang's place in the record books was fully and formally acknowledged. This delayed recognition is not unusual in science. Discoveries that depend on precise measurements across multiple wavelengths, made by different instruments over many years, rarely announce themselves with immediate clarity. The significance of the boomerang emerged the way most deep scientific understanding emerges, incrementally, through the patient layering of evidence. Each new observation added weight to what was already suspected, until the weight became undeniable. By 2013, there was no longer a reasonable scientific case to be made against it. The Boomerang Nebula was the coldest known natural object in the observable universe, and the record was secure. But a record, by its nature, invites a question. If the Boomerang is the coldest natural place we know of, does that mean it is the coldest natural place that exists? Are there other candidates, perhaps undiscovered, that might one day claim the title? And beyond nebulae, are there other environments in the cosmos, different kinds of objects, different physical settings, where extreme cold might also be found? The honest answer is that the Boomerang's record is a record of our current knowledge, not necessarily of what the universe contains in its entirety. Other preplanetary nebulae do exist throughout the Milky Way, and most of them are significantly warmer than the Boomerang. The typical temperature range for the cold molecular gas in protoplanetary nebulae falls somewhere between 10 and 30 Kelvin, still extraordinarily cold by any human standard, still cold enough to freeze many gases onto grain surfaces, but well above the CMB temperature and nowhere near the Boomerang's 1 Kelvin. The processes that produce cold in these objects are similar in kind to what operates in the Boomerang, but not in degree. The combination of outflow speed, mass loss rate, and, almost certainly, the binary interaction that drove those parameters to such extremes in the Boomerang appears to be rare. Not impossible to replicate elsewhere, but rare. And yet, the Milky Way contains hundreds of billions of stars. Even rare events, across those numbers, happen more than once. It is entirely plausible, astronomers acknowledge, that other protoplanetary nebulae exist somewhere in the galaxy with conditions similar to the Boomerang, objects where a binary interaction drove an extraordinary outflow, where adiabatic cooling dropped the temperature below the CMB, where frozen molecules coat the surfaces of drifting dust grains in conditions as extreme as anything the Boomerang currently hosts. We simply have not found them yet. The Boomerang was discovered because astronomers looked in the right place with the right instruments at the right time. The galaxy is large, and our surveys of its stellar populations, while increasingly comprehensive, are still far from complete. There are regions of the Milky Way that remain poorly mapped, particularly at the distances and wavelengths relevant to cold molecular gas. The ALMA Observatory has opened new possibilities for finding and characterizing cold nebulae, but its observing time is limited and the sky is vast. So the Boomerang's record may be a record of the observed universe, rather than the actual universe. It is the coldest natural place we have confirmed. Whether it is the coldest natural place that exists is a different question, and one that honesty requires us to leave open. Beyond protoplanetary nebulae, the search for extreme cold in nature leads to some unexpected places. Among the thousands of exoplanets, planets orbiting stars other than our Sun, discovered in recent decades, a small number inhabit environments of quite remarkable cold. Planets far from their host stars, or orbiting very dim and low-energy stars, can have surface temperatures that drop to extraordinarily low levels. Some of the coldest known exoplanets are so-called rogue planets, or free-floating planetary mass objects, bodies of planetary mass that have been ejected from their original star systems and now drift through interstellar space, unbound to any star. Without a star to warm them, these objects receive no stellar radiation at all. Their temperature is set by whatever residual internal heat they retain from their formation, and by the ambient temperature of the interstellar medium around them. Over time, they cool toward the background temperature of space. Old, cold rogue planets drifting in the interstellar medium may have surface temperatures approaching the ambient interstellar temperature, perhaps 10 to 30 Kelvin, or in some cases potentially lower. These are not objects we have measured in detail. They are, by definition, extremely difficult to detect, being dark, cold, and unilluminated by any nearby star. But their existence is well established theoretically, and a number of candidate free-floating planetary mass objects have been detected through gravitational lensing and infrared surveys. They represent a population of cold, dark wanderers filling the galaxy in numbers that may exceed the number of stars, and their surfaces, if surfaces they have, are among the coldest solid environments nature is likely to produce. There are also brown dwarfs, objects too massive to be planets but too small to sustain hydrogen fusion like true stars, that, in their oldest and coolest forms, have surface temperatures approaching room temperature or even below. The Y-class brown dwarfs, the coldest known class of these objects, have measured atmospheric temperatures as low as a few hundred Kelvin in some cases, and theoretical models suggest that the oldest and most massive brown dwarfs could, given enough time, cool to even lower temperatures. These are not approaching 1 Kelvin, not remotely, but in the context of stellar and substellar objects, they represent one extreme end of the natural temperature distribution. And then there is the broader cosmic environment. We have discussed the intergalactic medium, the interstellar medium, dark molecular clouds. But the universe also contains vast underdense regions, cosmic voids, the enormous empty spaces between the filaments and sheets of galaxies that make up the large-scale structure of the cosmos. These voids contain almost no matter. The galaxy density within them is extremely low, and the heating effects of nearby stars and active galactic nuclei are correspondingly weak. In the deepest and most isolated parts of these cosmic voids, the temperature of any matter present would be set almost entirely by the cosmic microwave background, 2.7 Kelvin, with very little additional heating to push it above that floor. To find anything in the natural universe that falls below that floor, below 2.7 Kelvin, requires the kind of active, dynamic process that the boomerang provides. Passive environments, no matter how remote or empty, cannot fall below the CMB temperature through inactivity alone. The CMB is everywhere. It warms everything, just barely, just enough to set a floor. Crossing below that floor requires a mechanism, a process, an active departure from equilibrium. The boomerang's rapid adiabatic expansion is such a mechanism. It is, as far as we know, the only natural mechanism that has managed to produce it at the scale of a nebula. It is instructive to contrast the boomerang with something at the opposite extreme, not to diminish the cold, but to appreciate the full range of temperatures the universe contains. The Orion Nebula, one of the most photographed and celebrated objects in the night sky, is a region of active star formation roughly 1,344 light-years from Earth. At its heart, young, massive, energetic stars are pouring ultraviolet radiation into the surrounding gas, ionizing it, heating it, driving it into luminous activity. The hottest regions within the Orion Nebula reach temperatures of around 10,000 Kelvin. The most energetic parts of the ionized gas can exceed that. 10,000 Kelvin, compared to 1 Kelvin. The Orion Nebula and the Boomerang Nebula are both clouds of gas in the Milky Way, both within a few thousand light-years of Earth, both products of stellar physics. And between them they span a temperature range that encompasses almost the entire domain of naturally occurring gas temperatures in the galaxy. One is a nursery, blazing with the energy of newly born stars. The other is a death, cooler than the universe around it. The contrast is not just numerical. It feels, in some way, almost narrative, the hot brightness of beginnings against the cold quiet of endings. The universe, it turns out, is a place of extraordinary thermal range. From the interior of massive stars where temperatures reach billions of Kelvin, to the outer reaches of dying stellar envelopes where the temperature barely exceeds absolute zero, the cosmos spans a thermal landscape almost incomprehensible in its breadth. And we, on our small, temperate planet, exist in a narrow band somewhere in the middle, warm enough for liquid water, cool enough for complex chemistry, occupying what amounts to a tiny climatic niche in a universe defined by extremes. But here is something worth pausing on. When it comes to cold, the universe's record holder, the Boomerang Nebula at 1 Kelvin, is not, in fact, the coldest thing that currently exists. Because in laboratories on Earth, in buildings that could fit on a university campus, human beings have created temperatures colder than the coldest known natural place in the observable universe. That sentence deserves a moment to settle. The tools of modern low-temperature physics, laser cooling, evaporative cooling, dilution refrigerators, magnetic traps, have allowed physicists to cool small samples of matter to temperatures measured not in Kelvin but in millikelvin, microkelvin, and even nanokelvin. 1 millikelvin is 1,000th of a Kelvin. 1 microkelvin is 1 millionth. 1 nanokelvin is 1 billionth. Experiments working with ultra-cold atomic gases have achieved temperatures in the picokelvin range, trillionths of a degree above absolute zero. These are temperatures so low that they are essentially unreachable by any natural process we have observed. The samples involved are tiny, a few million or billion atoms, occupying a space smaller than a grain of rice, suspended in a vacuum chamber and manipulated with lasers and magnetic fields. These are not large, macroscopic objects cooled to extreme temperatures. They are carefully isolated quantum systems, prepared with extraordinary precision for the purpose of studying the behavior of matter at the quantum mechanical limit. But the temperatures are real, and they are lower, far lower, than the 1 Kelvin of the Boomerang Nebula. Beneath the Earth's surface, in the tunnels and vaults that house some of the world's most sensitive physics experiments, similar cold is being maintained. The Large Hadron Collider at CERN operates its superconducting magnets at around 1.9 Kelvin, slightly warmer than the Boomerang, but close. Dilution refrigerators used in quantum computing research regularly achieve temperatures below 10 millikelvin. These machines are strange and beautiful objects in their own right, elaborate systems of concentric chambers, cryogenic fluids, and precisely engineered heat exchangers, all working together to remove thermal energy from a small space at the center. There is a certain poetry in the parallel. Cryogenic research, in its practical applications, shares something of the same essential challenge that the Boomerang Nebula represents in nature: the problem of removing heat faster than it arrives, of maintaining a state of extraordinary thermal stillness against a universe that is constantly, gently trying to warm everything back toward equilibrium. In the laboratory, we fight that tendency with technology. We insulate, and pump, and cool, and control with extraordinary precision. In the Boomerang, a dying star fights it with sheer physical scale, billions of tons of gas expanding at 164 kilometers per second, overwhelming the universe's gentle background warmth through the brute physics of rapid expansion. Different mechanisms, similar results. And in both cases, the cold that is achieved is not really an absence of something. It is a presence, a state of extraordinary physical stillness, a condition in which the random thermal motion of matter has been reduced as close to zero as the laws of physics permit. Cold, understood this way, is not nothing. It is one of the most carefully achieved, carefully maintained, and scientifically productive states that matter can occupy. Whether it is produced by a dying star in the constellation Centaurus, or by a dilution refrigerator in a laboratory beneath a Swiss meadow, the fundamental pursuit is the same: stillness. Quiet. The closest approach to absolute zero that physics allows. The pursuit of cold, in a laboratory context, is not an end in itself. The extraordinary effort required to cool matter to millikelvin and microkelvin temperatures, the elaborate equipment, the carefully engineered isolation, the constant vigilance against any source of heat that might disturb the experiment, all of it is justified by what becomes possible at those temperatures. Cold, at the quantum scale, is not just an absence of warmth. It is a condition that unlocks physical phenomena that simply do not exist at higher temperatures, phenomena that have already changed the world and may change it further still. Superconductivity is perhaps the most familiar example. Certain materials, when cooled below a critical temperature, lose all electrical resistance entirely. Current flows through them without any energy loss whatsoever, a property that has enabled MRI machines, particle accelerators, and increasingly forms the basis for quantum computing hardware. The superconducting magnets of the Large Hadron Collider, the quantum processors being developed in research facilities around the world, the sensitive detectors used in medical imaging, all of them depend, in one way or another, on the physics that extreme cold makes possible. Cryogenic research has also given us precision timekeeping, ultra-sensitive gravitational detectors, and tools for manipulating individual atoms with a control that would have seemed like science fiction a few generations ago. The atomic clocks that underpin GPS navigation, financial transaction timing, and telecommunications networks owe their extraordinary precision to the principles developed through decades of cold atom research. The ability to cool atoms to near stillness and then probe their quantum states with laser light has produced timekeeping accurate to within a second over billions of years, a level of precision almost too fine to meaningfully visualize. Beyond these practical applications, cryogenic research opens windows into fundamental physics. At very low temperatures, quantum mechanical effects that are normally averaged away by thermal noise become dominant and observable. Matter can enter exotic states, Bose-Einstein condensates, superfluids, strange topological phases, that reveal aspects of the quantum world that no other experimental approach can access. These states of matter are not just curiosities. They are laboratories within laboratories, environments where physicists can study the behavior of matter at its most fundamental, most quantum mechanical level, and extract insights that may eventually reshape our understanding of reality at the smallest scales. One experiment in particular captures the ambition of this pursuit in a way that is worth describing in detail. In Bremen, Germany, researchers working with a facility known as the Bremen Drop Tower conducted an experiment in which a small cloud of atoms was cooled to extraordinary temperatures and then allowed to expand in free fall. The tower allows objects to fall freely for several seconds, creating a brief period of effective weightlessness. In that window, with the disturbing effects of gravity temporarily removed, the ultra-cold atomic cloud could expand in ways that would be impossible under normal laboratory conditions. The temperatures achieved in this experiment pushed into the picokelvin range, trillionths of a degree above absolute zero. Colder than anything the natural universe is known to produce. Achieved in a tower in a German city, by a team of physicists with lasers and magnetic coils in a carefully engineered vacuum chamber. The result was remarkable not just as a temperature record but as a demonstration of what becomes observable at these extremes. The expanding cloud of atoms, freed from gravity and cooled to near absolute stillness, began to exhibit quantum mechanical behavior on a macroscopic scale, the kind of behavior usually visible only at the atomic level, now playing out across a cloud large enough to be observed and measured in detail. Cold, in this context, became a microscope, a tool for seeing the quantum world at a scale normally hidden. But even this achievement was not the final word. In 2018, an experiment left the surface of the Earth entirely. The Cold Atom Laboratory, known by its acronym CAL, is a compact scientific instrument developed by NASA's Jet Propulsion Laboratory, designed specifically to produce and study ultra-cold quantum gases in the unique environment of space. It was launched to the International Space Station in May 2018, becoming the first facility for ultra-cold atom research ever operated in orbit. And what it achieved, in the environment of the space station, was something that no ground-based laboratory had managed to sustain. Space offers an advantage that no Earth-based laboratory can fully replicate. On the ground, gravity is always present, and it affects ultra-cold atomic clouds in ways that limit how long experiments can last and how cold they can effectively reach. An ultra-cold cloud of atoms will sag under its own weight, distorting the experiment and introducing unwanted effects. Even in the Bremen Drop Tower, the period of weightlessness lasts only a few seconds. On the International Space Station, in continuous free fall around the Earth, that weightlessness is effectively permanent. The Cold Atom Laboratory can hold its ultra-cold atomic clouds and magnetic traps for far longer than any ground-based facility, allowing the cooling and observation to proceed without the interference of gravitational distortion. The result is temperatures that are, by any reasonable measure, the coldest known spots in the universe, colder than the Boomerang Nebula, colder than the Bremen drop tower experiments, colder than anything that has ever been measured or confirmed anywhere. The Cold Atom Laboratory has cooled atoms to temperatures of around 1/10 of a degree above absolute zero. Written out, that is 0.0000000001 Kelvin. The Boomerang Nebula, at 1 Kelvin, is 10 billion times warmer than what Cal achieves aboard the space station. That comparison is worth sitting with. The coldest known natural place in the observable universe, a cloud of gas colder than the background temperature of the cosmos, produced by one of the most extreme stellar processes we have ever observed, is 10 billion times warmer than what a small scientific instrument, the size of a mini fridge, is producing in a laboratory floating 400 kilometers above the Earth's surface. It is one of those facts that quietly reframes the relationship between the natural universe and human scientific achievement. Nature, for all its scale and power, works within the constraints of available physical processes. The boomerang is extraordinary precisely because adiabatic expansion in a dying star is an unusually effective cooling mechanism in the natural world. But it is still a macroscopic, thermodynamic process. Human cold atom physics operates in a different regime entirely, one where individual atoms are manipulated with exquisite precision, where quantum mechanics is not a background consideration but the direct subject of study, and where temperatures that have no natural analog can be achieved and sustained. The International Space Station, in this sense, is not just a platform for Earth observation and materials science. It hosts, in the Cold Atom Laboratory, the coldest known location in the universe. A small metal box, orbiting overhead right now, maintaining a temperature that no star, no nebula, no dark molecular cloud has ever naturally produced. At these temperatures, the atoms inside the Cold Atom Laboratory are moving with extraordinary slowness. At room temperature, atoms in a gas move at hundreds of meters per second, colliding constantly, vibrating with the energy of thermal motion. As temperature drops, that motion slows. At a few Kelvin, atoms move at a few meters per second, walking pace. At millikelvin temperatures, they crawl. At the temperatures achieved by Cal, the atoms are moving at speeds measured in millimeters per second, or even slower. They are, for all practical purposes, nearly stationary. Not quite at absolute zero, not quite motionless, quantum mechanics forbids complete stillness, even at absolute zero, through what is known as zero-point energy, but as close to stillness as anything has ever been measured to be. In this state of near-perfect thermal quiet, the atoms begin to behave in ways that have no classical analog. They lose their individual identities, in a sense, and begin to act as a single coherent quantum entity, a Bose-Einstein condensate, a state of matter that was predicted by Einstein and Satyendra Nath Bose a century ago and first created in a laboratory in 1995. In this state, quantum mechanical wave functions overlap and merge, and the collective behavior of the atoms encodes information about the quantum world that no other experimental technique can access. This is what the Cold Atom Laboratory was built to study. Not just to achieve a low temperature, but to use that temperature as a gateway into a regime of physics that the universe, left to its own devices, does not naturally produce. A regime of perfect quantum coherence, of near absolute stillness, of matter behaving in ways that the laws of physics permit but that no natural process has ever, as far as we know, managed to create. The coldest place in the universe is not in a distant nebula. It is not in the intergalactic void. It is in a laboratory, in orbit, built by human hands, maintained by human ingenuity, and dedicated to the patient, meticulous study of the universe at its quietest and most fundamental. There is something both humbling and quietly exhilarating in that. We live on a warm, noisy, thermally active planet, bathed in the radiation of a nearby star, surrounded by an atmosphere that keeps us comfortable and alive. And from that warm, bright, living world, we have reached outward and downward simultaneously, outward to discover the coldest natural place in the observable universe, and downward, toward absolute zero, to create something colder still. The universe sets the floor. And then, carefully and persistently, we go beneath it. When atoms are cooled to within a fraction of a degree of absolute zero, something happens that sits at the boundary between physics and philosophy. Individual atoms, each one a distinct particle, with its own position, its own momentum, its own quantum state, begin to lose their separateness. Their quantum mechanical wave functions, which describe the probability of finding each atom at any given location, spread out and begin to overlap with the wave functions of neighboring atoms. And when the temperature drops low enough, something extraordinary occurs. The overlapping wave functions merge into a single, coherent quantum state. The individual atoms, in a very real physical sense, become indistinguishable from one another. They stop behaving as a collection of separate particles and begin behaving as a single unified quantum entity. This state of matter is called the Bose-Einstein condensate. It was predicted mathematically in the 1920s by Albert Einstein and the Indian physicist Satyendra Nath Bose, working from the implications of quantum statistical mechanics. Their calculations suggested that if a gas of certain types of atoms, atoms with integer quantum spin, known as bosons, were cooled to sufficiently low temperatures, the individual particles would collapse into the same ground quantum state and behave collectively. The prediction was elegant and theoretically well-grounded, but for 70 years it remained exactly that, a prediction. The temperatures required were simply too low to achieve with available technology. In 1995, physicists Eric Cornell and Carl Wieman at the University of Colorado, and independently Wolfgang Ketterle at MIT, created the first Bose-Einstein condensates in a laboratory, using laser cooling and magnetic trapping techniques to bring small clouds of atoms to temperatures in the nanokelvin range. The achievement earned Cornell, Wieman, and Ketterle the Nobel Prize in Physics in 2001. What had been a mathematical prediction for 7 decades became a physical reality, a new state of matter, created and observed and studied on a laboratory bench. What makes a Bose-Einstein condensate so remarkable, beyond the extraordinary temperature required to create it, is what it reveals about the nature of matter itself. In everyday life, quantum mechanical effects are hidden. The thermal noise of room temperature matter averages out the quantum behavior of individual particles, leaving us with the classical, predictable world we experience. But in a Bose-Einstein condensate, that thermal noise is almost entirely gone. The quantum nature of matter is no longer hidden. It is the dominant reality. The condensate flows without friction, responds to perturbations in ways that reflect pure quantum mechanics, and encodes information about the quantum world in a form that can be directly observed and measured. The Cold Atom Laboratory on the International Space Station creates Bose-Einstein condensates in microgravity, where the absence of gravitational distortion allows the condensates to be held and studied for far longer than is possible on the ground. In this environment, physicists can observe the quantum behavior of these cold atom clouds with a clarity and duration that opens genuinely new scientific territory. Questions about quantum mechanics, about the nature of space and time at the smallest scales, about the behavior of matter at its most fundamental, all of these become more accessible in the near-perfect stillness of an ultra-cold condensate floating in orbit. This is, in the deepest sense, what the pursuit of cold has always been about. Not just the temperature itself, but what the temperature makes visible. Each step down toward absolute zero has revealed something new states of matter, new physical phenomena, new windows into the underlying structure of reality. The Bose-Einstein condensate is perhaps the most profound of these revelations so far. A state in which matter stops being many things and becomes, briefly and beautifully, one thing. A state that the universe does not naturally produce anywhere we have found, but that arises inevitably from the mathematics of quantum mechanics when the conditions are right. We made the conditions right. That is, when you consider the full arc of what it took, the physics, the engineering, the decades of accumulated knowledge, a genuinely remarkable thing. And yet, for all the wonder of what human technology has achieved in the cold laboratories of Earth and orbit, the universe beyond our planet has its own lessons to teach. The Boomerang Nebula, for all that it is surpassed in temperature by our best instruments, remains scientifically invaluable in ways that no laboratory can replicate. Studying the boomerang helps us understand how stars like our Sun die. The processes unfolding in its outflowing gas, the mass loss, the shaping of the nebula by stellar winds, the chemistry of molecules freezing onto dust grain surfaces, all of these are processes that occur, in various forms, in the final stages of stars throughout the galaxy. By observing the boomerang in detail, astronomers gain direct evidence about the mechanisms of stellar mass loss, the dynamics of bipolar outflows, and the physical conditions that govern the transition from red giant to planetary nebula to white dwarf. These are not abstract questions. They are questions about a life cycle that operates at enormous scale throughout the universe, producing the chemical elements that eventually find their way into planets, atmospheres, oceans, and living things. More personally, the boomerang helps us understand what our own sun will one day become. The star at the center of the boomerang was, in all likelihood, a star not entirely unlike ours, a main sequence star, burning hydrogen, warming whatever surrounded it for billions of years. And now it is in its final phase, shedding itself into space, creating in its ending the most extraordinary cold we have ever measured in nature. Our sun will follow a broadly similar path. Not identically, the details of stellar evolution depend sensitively on mass and composition, and the boomerang's extreme behavior may reflect the influence of a binary companion that our sun does not have. But the broad arc is the same. Red giant. Mass loss. Planetary nebula. white dwarf. When we look at the Boomerang Nebula, we are looking at a possible future. Not our personal future. This will unfold billions of years from now, long after any trace of present human civilization has faded. But our solar system's future, in a meaningful astronomical sense. The sun that warms us, that drives our weather, that has sustained life on this planet for billions of years, will one day exhale its outer layers into space in a cloud not unlike the one we have spent this time exploring. It will cool. It will expand. And somewhere in that future cloud, the same physics that make the boomerang so cold may operate in some form, gas expanding outward, molecules freezing, the last warmth of a stellar life dispersing into the dark. There is something both sobering and, in its way, peaceful about that. The sun's eventual end is not a catastrophe in any human sense. It is simply the completion of a very long natural process. Stars are born, burn, and die. They return their material to the interstellar medium, enriched with elements forged in their cores, to be gathered again into new clouds, new stars, new planets. The boomerang is one chapter in that cycle, an extraordinarily cold chapter, or record-breaking chapter, but still part of the same ongoing story that has been playing out since the first stars ignited in the early universe. Looking outward at objects like the boomerang is, ultimately, a humbling experience. Not in a diminishing way, not in the sense that it makes human concerns feel trivial or small, but in the deeper sense that it reminds us, gently and unmistakably, that we are part of something vastly larger than ourselves. We live on a warm, bright, living world, surrounded by complexity and beauty. And surrounding that world, at distances that make our largest instruments feel modest, is a universe of extraordinary range and strangeness. Nebulae colder than the cosmos itself. Stars dying in slow exhales of frozen gas. Dark molecular clouds where temperatures hover near absolute zero. And beyond all of that, the quiet, ancient background radiation of the Big Bang, threading through everything, the faintest possible warmth filling the largest possible space. We did not have to find any of this. For most of human history, we did not know any of it existed. The Boomerang Nebula drifted cold and silent in Centaurus for thousands of years before anyone on Earth had the instruments to detect it, let alone understand it. The universe kept its secrets patiently, as it always has, and revealed them only when we built the tools and asked the right questions. And there are more secrets still. The boomerang may be the coldest natural place we know of, but it is almost certainly not the most surprising thing the universe contains. Every generation of astronomers has found something that the previous generation did not expect, something that required new thinking, new frameworks, new instruments, new ways of understanding what space and time and matter actually are. There is no particular reason to think that process is over. The universe is not running out of surprises. We are simply still building the tools to find them. The cold places of the universe, from the shadowed craters of the Moon to the frozen surface of Pluto, from the dark molecular clouds of the Milky Way to the extraordinary stillness of the Boomerang Nebula, are not just extreme environments to be catalogued and set aside. They are windows. Each one reveals something about the physics of matter, the chemistry of molecules, the life cycles of stars, and the deep structure of the cosmos that warmer, brighter, more familiar environments cannot show us. Cold, in this sense, is not an absence. It is a perspective. A way of seeing the universe that complements and enriches every other way of looking. And perhaps that is the most fitting thought to carry away from this long journey through the coldest places in existence. That the universe, in all its thermal extremity, from the billion-degree cores of massive stars to the 1 Kelvin stillness of a dying stellar cloud, is not a collection of separate, unrelated phenomena. It is a single, connected, endlessly evolving system. Everything in it is related to everything else. The cold of the boomerang was made possible by the heat of the star that created it. The frozen molecules on its dust grains were forged in the nuclear furnaces of earlier stars. The background radiation that the boomerang is colder than was produced by the Big Bang that created everything, 13.8 billion years ago. We are, all of us, every warm living thing on this warm living planet, part of that same system. Made of the same atoms that cycle through stars and clouds and nebulae. Warmed by the same kind of nuclear fire that once burned in the heart of the boomerang's central star. Alive in a universe that ranges from the almost unimaginable heat of stellar cores to the extraordinary, quiet cold of a pale hourglass-shaped cloud, 5,000 light-years away, slowly exhaling into the dark. The universe is very large. And very cold in places. And full, still, of things we have not yet found. That seems like a good reason to keep looking.